We're going to start Unit 3 here. Organic chemistry. Okay. Organic chemistry, the study of carbon-based molecular compounds. We're going to be dealing all with carbons, a lot of carbon stuff, a lot of hydrogen stuff, but organic chemistry is the study of carbon-based molecular compounds. Nearly all carbon-containing compounds are classified as organic, so most of them are classified as that. There are some exceptions which you should know, okay? So things like, for example, things that are not organic, and this will be definitely a question. They always give you something like this here. Anything to do with carbonate, for example, CO3 2- is not organic. It's actually inorganic, of course, as it says here. Cyanides, so Cn-, okay, carbides, oxides of carbon, so carbon monoxide, carbon dioxide, things like that are not organic. Okay, here's some examples of inorganic compounds. So sodium carbonate, hydrogen cyanide, calcium carbide, and carbon dioxide, for example, are some that are not organic. Okay, like I said, make sure you know that because I guarantee you that's going to be a question. Always is, always will be. Diversity of organic compounds is based on several factors. When you think about carbon, okay, and you should know this from last year, of course, carbon has a large bonding capacity. It's got a bonding capacity of 4, yes? Carbon has 4 valence electrons. Look, 1, 2, 3, 4. It's got 4 valence electrons. It can have 4 things bonded to it, okay? So we always look for, kind of remember that's the octet rule if you remember from Chem 20. So we're always looking for 4 things around each carbon. And it might combine with another carbon and another carbon. Carbon has the ability to form long chains or rings of many different lengths. So you might get 10 carbons in a row, for example, or 7 or 8, or you might get them in a ring structure. So they may come in a ring. All right. Carbon has a great ability to form strong single, double, triple covalent bonds. We're talking about molecular compounds in most cases here. Organic compounds, so molecular sharing electrons. And so, for example, if you bond a carbon to another carbon, right, you could maybe have that as a double bond, a single bond, or maybe even a triple bond in some cases. Okay? These factors allow carbon-based compounds to exist as isomers. Now, this is something that you probably haven't heard this term for quite some time. Isomers is something that, you know, I talk about in Unit 1 at the very beginning of the year in Chem 20. Isomers have the same formula, but a very different structure, which usually leads to different properties as well. Okay, so it has the same molecular formula. Like for example, we're going to do one with butane, C4H10, and there's another C4H10 structure, but it's methylpropane. Okay, so even though they have the same number of carbons and hydrogens, they can arrange themselves differently. All right. These two isomers, for example, isomers. Let me just get rid of this for a second here. Here's 2 isomers of C4H10. One is called butane, okay, which would be butane gas. C4H10 has 4 carbons. Now remember, the idea here is with all the carbons here, all right, is that we have 4 around this carbon, 4 bonds around here, 4 bonds around this carbon, and 4 bonds around there, because remember each line represents 2 electrons being shared, yes? Correct? Okay. Same thing here. We got 4 around each one, but it's arranged a little differently, you'll see. Okay, 4 carbons. If you count up all the hydrogens, there's 10 of them, trust me. Okay, 4 there, 4 there, 4 there, and then if you look up here, basically there's 4 around that carbon there. And of course, anywhere you look, you got 4. Remember, hydrogen only needs 2 around it, right? 2 electrons to be shared. That's all it has room for. Hydrogen only forms 1 bond. Okay? So, here's butane, C4H10. Here's methylpropane, C4H10. Both have the same formula, C4H10. Very different properties. Okay? And we're going to talk about those here. Because of their different structures, isomers have different properties. Okay? We talked about this in Chem 20 even, in fact. Most of these, and this would be back to Unit 1, where we talk about things like London forces and dipole-dipole and hydrogen bonding and stuff like that. Remember that? Okay? Well, that's what we're going to talk about here, because anytime you see, what's your key here when we talk about these intermolecular forces, what holds one molecule to another molecule, right there, boiling point is a prime example of intermolecular force. What holds one C4H10 to another C4H10 to another one, to another one, to another one? Well, that's intermolecular forces. With these compounds, usually London forces plays a fairly big role because most of these are nonpolar compounds in most cases. Butane has a boiling point of about -0.5, so let's just call it 0 for convenience sake. So it has a boiling point of 0 basically. Okay. Methylpropane has a boiling point of -12. So the point here is, even though they have the same formula, C4H10, they have quite a bit different boiling points. One boils at -12, one boils at about 0. Okay? That's 12 degrees difference. That's a difference, right? I mean, that's not substantial, but it's enough, right? And the reason is, we go back to here, for example, and we think about back to Chem 20, and we say, well, the reason is because London forces are based on two things, size and shape, right? And because these London forces here, obviously C4H10 and C4H10, they're going to have the same number of electrons floating around and around, yes. That's one of the things, size. The other thing is shape. That one's kind of cylindrical, yes? Or linear-ish, I guess you could say. And linear is better, yes, for London forces, because you get, here's another C4H10 right here, you just don't see it. You get a lot of surface area between the two of them that contact each other, right? And because there's a lot of surface area, they hold together better usually, because electrons, these electrons affect these electrons, et cetera, so they can stick together very well. Okay? That's why the boiling point's a little bit higher. It's at 0. And that's why this one's lower, because this one's more of a spherical kind of shape. So if you want to put another one next to this, where are you going to do that? Well, let's see here. Let me just draw this down here. What are you going to do? You're going to do another one like that, right? Well, you only got that much surface area between the two of them. A little harder to get that same contact, Here's linear, spherical. They sit on top of each other nicely. Here's, or cylindrical, I should say. Spherical kind of looks like this, right? You only get that much contact between each other. So that's the difference between these two. And of course, which one's easier to break? Well, this one is, because you only have this much contact between them. So I don't have to put as much energy in to break that intermolecular force there. Yes? Okay. Whereas I have to put more energy in. This boils at -12 degrees Celsius. So I start, let's say, at -25. I turn on the stove, and -20, -15, -12. Hey, it boils. It breaks apart. And then I keep going. -10, -5, 0, right? Roughly. Then that finally breaks apart. So that requires more energy because they're stuck together better, right? So London forces, yes? So, like I said, the structures can lend themselves to different properties, and that's why we have different names for them. And that's what we're going to learn on Monday, is how to name these different structures, okay? So, we talked about that there. Now, let's see here. Butane's cylindrical shape results in stronger London forces that is found between the molecules and more spherical methylpropane. Drawing organic compounds. So, we're going to draw numerous compounds here. You're going to get tired of this, but it's fun, okay? First of all, one of the ways you can, I don't know, this is not really a drawing, I guess. This would be a representation of C5H12, for example. How would I show you C5H12? I could just use the molecular formula. So I could say, hey, this is C5H12. C5H12 tells you the number of carbon atoms, tells you the number of hydrogen atoms, but makes no attempt as to what does this structure actually look at. Does it have 5 carbons in a row? Don't know. Possibly, that's one option. Does it have 4 in a row and then another carbon sticking up somewhere? Maybe. Does it have 3 in a row and 2 carbons sticking up and down or something like that? Possibly, I don't know. So this one's not very good other than telling you just the general formula, right, of this. So that's the empirical molecular formula. Expanded helps a little bit because it shows the groupings of atoms. Bonds are assumed to exist between atoms here. So remember, right? Let me just get rid of this for a second here too. When you think about this here, you have to understand, of course, guys, when I write CH3 out, I don't do this. Here's CH3, yes? Can I put a carbon there? No, because hydrogen can only form one bond, yes? Okay, so obviously that's not the structure, right? When they talk about CH3, what do I have to do? I have to do this, and then I probably have to do what? Well, another carbon here with another 2 hydrogens belonging to that one, and so on and so on. Okay? All right, we'll stop there.